Welcome back, everybody. We're continuing with Chapter 6 notes on forces. And up to this point, we have just kind of described forces as kind of a general concept, and have also gotten into describing Newton's first law, which is we'll oftentimes call it the law of inertia, which describes the fact that objects in motion stay in motion, objects at rest stay at rest, unless acted upon by an outside force. And so anything can have anything that has a constant velocity, whether it's at rest or it's in motion with a constant velocity, is said to have inertia. Now we're at Newton's second law, and this is one where, in comparison to Newton's first law is kind of conceptual, but Newton's second law actually has a mathematical application to it, and it's this equation right here, and that is the relationship of force to mass and acceleration. Now, force, you'll notice, has the arrow over top of it right here, so force is a vector, and what that's equated to is the mass of something, which is not a vector. Mass is just a quantity. It's an amount of matter something has, times the acceleration. Of course, we know acceleration is a vector, and it has that arrow over it as well, indicating that. And so that force is going to be applied in the same direction as that acceleration right there. You may be wondering, and I think we mentioned this before, but if you couldn't remember, if you may be wondering what this funny-looking symbol is right here, this is a Greek letter sigma, which really means the sum of, S-U-M, right? So that's that right there. So there could be a number of forces acting on something, but if you sum them all up, if you take all the pluses and subtract all the minuses, it really winds up being the sum of all the forces. Oftentimes we call it the net force. The net force. I'll write that in green right here. All right, also known as net force. Or, well, the sigma means net, and of course force means force. So this equation right here is probably one of the most important mathematical equations to be probably to be ever created. Obviously by Newton, possibly even by anybody. So very much like when we did projectile motion and we did the two-dimensional kinematics, when we look at problems involving force, we can think of this in the same way as well. And you'll notice these two equations right here are basically the same thing as what we just talked about. It's net force equal to mass times acceleration, but it has the subscripts x and y right here. Forces in the y don't interfere with the forces in the x, and forces in the x don't interfere with the forces in the y. And so we can think of these two forces as being independent, or you might say these directions as being independent of each other. It's very important to remember as we're going to be summing up forces that are at right angles to each other. So this is just kind of a sort of a heads up as to how to solve force problems. First of all, we want to sketch a free body diagram. Now, we haven't really done much of that, but I'll show you a little bit later what that is. A free body diagram is really simply a diagram, like a point diagram, that shows all the forces acting on an object as if it were a point. Let's say you have a ball, okay, and a soccer player kicks a ball. All right, here's a ball right here, and then the soccer player's foot is coming down next to it. The foot is applying a force to that ball. All right. Well, a free body diagram would really have the ball represented as a dot. Okay, and the force would be actually coming out of this end, because even though the force is applied from the kicker's foot behind the ball, it's really propelling the ball, here represented as a point mass. It's really propelling the ball in that direction. Right there. So we'll do more with free body diagrams, and I even actually kind of do a variation on that as well. So what a free body diagram is a sketch. Don't sell yourself short on this part right here. do a sketch so you can sum up all of your forces. The coordinate system means you've got the x direction and the y direction, even an in-between direction as well. But make sure you sketch your forces in your x and in your y direction. This ball right here is only experiencing a force in the x direction. All right, but there could be a y direction if some other force were applied to it. Make a vector table like this right here. All right. So we're saying, okay, this is the sum of all the forces in the x direction. This is the sum of all the forces in the y direction right here. So add all your forces in the x. So we've got some positive force in the x1, and we've got some other positive force in the x2, and oh, we've got some negative force in the x direction 3 right here. So we're going to add all those up, and we're going to equate that to mass times acceleration in the x direction. Same thing with the y. All right, let's say we have a negative force in the y direction. We'll call that force y1, and another negative force in the y direction. That's force y2, and so maybe so well the positive. I'm doing the opposite right here. I'm doing a positive force in the y direction 3. These are 3 different forces. We add them all up, sum them all up, and then that net force, that should be a y right there, sorry. These are going to be the net force in the y direction, and we're going to equate that to the mass times acceleration in the y direction right there. So this is how we're going to set them up when we do our problems. All right, so let's do this problem right here. We have Moe, Larry, and Curly. Now, if you don't know the Three Stooges, that's the names of the Three Stooges, kind of the old comedy act. And we're going to do this first example right here, and then do some other examples in subsequent videos. But we have them all exerting a force that is in this first scenario right here, scenario A. Each of them applies an 80.5 Newton force. Now, a Newton is the unit of force, a unit that we're going to use to describe force. You probably know Newton to be the last name is Isaac Newton, and of course it's named for him. A Newton is very much like a pound. A pound that is in the English system is a unit of force. Like when you step on a scale, here's your scale right here. You have some weight. Right? Your gravity pulls you down onto this scale right here. All right, so here's you standing right there on the scale. And the scale registers some sort of force that's measured in pounds. Newtons are the exact same thing as pounds. It's just the metric version of them. But it comes out to be about 1/4 of a pound for a Newton. All right, that's roughly what a Newton is. So it's less than a pound, but it's the same kind of measurement. It's a measurement of force. So we're going to be measuring all of our forces in Newtons. So in scenario 1, we have 3 forces here, Moe, Larry, and Curly, all applying a positive force. We'll call this the positive direction right here, because after all, here's our coordinate system. There's the origin, and here's positive x. They're all applying a positive force, positive 80.5, positive 80.5, and positive 80.5, all in the positive direction. All right, what we want to find out is what is the acceleration of the boat for part A. All right, and let's see, I'm going to go to the next slide right here to kind of write this out and show you how to set this up. But I got to remember what the part B is asking us. Okay, so part B is a little bit different. All right, so here's how we'd set it up. We have our, we're going to draw our free body diagram. Now, I said before that oftentimes free body diagrams are drawn as if, we'll just call this part A right here, as if it were a point mass. Sometimes I cheat a little bit and make it a boxy thing, like it's a boat or a car or a box, something like that. But for now, we'll do it as a point mass. And so we have force 1, in fact, I'll call it force M for Moe, is 80.5 newtons. Force L for Larry is 80.5 newtons, and force C C for Curly is 80.5 newtons as well. All right, and so we can write those three forces as such. I'm just going to write in red right here. So the net force, remember these are all positive forces, net force on the boat is going to be 80.5 plus newtons, plus 80.5 newtons plus 80.5, 80.5 newtons right here. We're going to add all those up. What do we get? That tells me this is 241.5 newtons, okay? That's our net force acting on this boat right here, okay? Net force acting on the boat. So the question is, what is the acceleration of the boat? All right, so that's our unknown right there that we want to find out. We're told in the previous problem, or I should say on the previous page, that the mass of the boat, and this is going to be important, mass of the boat equals 752 kilograms. All right, now that's going to be our main unit of mass when we do these kinds of problems right here. Kilograms, not grams, even though the grams is the base unit. Kilograms is going to be our main unit for this kind of problem. So we want to find our acceleration. Well, we know that the net force on the boat equals mass of the boat times acceleration of the boat. All right, so we have our net force right here. We have our mass. All we have to do is solve for acceleration. So the acceleration of the boat is going to be the net force on the boat divided by the mass of the boat. Okay, our net force is 241.5 newtons. Okay, that's our force value, and it has a mass of 752 kilograms. So that leaves us with an acceleration value of 0.32 meters per second squared. That is our acceleration of the boat right there. And if we were to go back and look at that, you have all the forces acting in the same direction on this boat, which is 752 kilograms is pretty heavy. It's pretty massive. It's about oh goodness, it's about a ton and a half in English units. But so that means that those forces of those three guys acting on the boat makes it accelerate, not very fast, but it is accelerating. But now we're going to see what happens if we have these forces acting against each other. So this is part B right here. All right, in part B, we have this boat. I'm going to make it point mass again, all right? Mo is one who is pushing in the positive direction. Force from Mo equals 80.5 newtons. But Larry and Curly, being kind of the dopey ones of the Three Stooges, if you've ever seen them, force of Larry equals, they're pushing in the wrong direction. They're pushing against Mo right here. So that's negative 80.5 newtons, and Curly's doing the same thing. Force from Curly equals negative 80.5 newtons. Okay, so now we're going to have a different net force on the boat. Net force on the boat is going to be, what is it, 80.5 newtons plus negative 80.5 newtons plus another negative 80.5 newtons right here. All right, so what's it come out to? Well, basically these two guys cancel out, and so we're going to have a net force in the negative direction of negative 80.5 newtons. That's our dotted line box right there, because that's really important, because the net force is one of the main things we want to find out right here. We're asked what the acceleration of it is now. All right, so we have two guys working against one guy right here. So once again, the net force on the boat equals the mass of the boat times acceleration of the boat. And so the acceleration is going to be the net force of the boat divided by the mass of the boat. And I should say this for part B, which is going to be different. All right, so The new net force on the boat is going to be negative 80.5 newtons, and it still has a mass of 752 kilograms. All right. So that leaves us with an acceleration of the boat in the negative direction. It's going to be negative we'll round up to 1.1 meters per second squared. That's our final answer. So these two knuckleheads right here are working against this guy, and so the boat's going to be moving in the opposite direction and kind of slowly because the net force is a less value. At least when they're all working together, they have a faster acceleration of 0.32 meters per second squared. So that's our first problem on equating force with mass and acceleration. And so we're going to try to do that kind of format in future problems as we go forward. So look for that in subsequent videos. So thanks for watching for the time being, and I'll see you in the next one.